Ready? The 1986 explosion at the Chernobyl nuclear plant in the former Soviet Union sent about 1,000 kilograms of radioactive cesium-137 into the atmosphere. The function f of x, if you remember, we mentioned that in applications, 0.5 raised to x divided by 80. No, not by 80, but by 30. Okay, it looked like 80. Describes the amount f of x, amount in kilograms, of the radioactive substance remaining in the Chernobyl x years after 1986, x number of years since 1986. If even 100 kilograms of cesium-137 remain in Chernobyl's atmosphere, the area is considered unsafe for human habitation. Find f of 80 and determine if Chernobyl will be safe for human habitation in 2066. So what do I have to do? What do you think? Plug it in indeed. 1,000 and 0.5 raised to 80 divided by 30. Let's put this in the graphing calculator. Please go to y equals. Clear if you have anything else in there, there is no need. And let's put in 1,000 in parentheses 0.5, close the parenthesis, power or caret, in parentheses, put x divided by 30. Just put the function itself, because I may want to test not just for 80, but I may want to test for more than just 80. So now let's go to second n table. And I'm going to punch in 80. I'm going to punch in, I don't know, 100. I'm going to punch in 120. And just take a look and see what happens. So 100 years since 1986, how many kilograms of cesium-137 are still in the atmosphere of Chernobyl area? 157.49. Will you tell those people, hey, if you still have your home over there, you can go back? No, you will not say that, because it's not safe for human habitation. What will you say after 100 years to their great-great or great-grandchildren, whatever? What would you say? It may be, if the model is still correct, it's under 100, you may consider.
How do you get to x?
Say it again?
How do you plug in x again?
It's this function, this key that has the variable x.
I mean, like, how do I?
Second in table,
Okay.
and you punch in. I punched in 80, 100, and 120. We only need 100. So the answer is 157.49 kilograms. You will not recommend them to go back. Here's another application of exponential functions. And that application is for interest compounded in two different ways. One, n times per year. And the second possibility is continuously. There are two different formulas. You do not have to memorize them. They will be given to you. The first one will be a equals p 1 plus r over n raised to nt. I'll explain what this all means. And a equals pe to rt.
Is this for natural or is this still common? Or is this something totally different?
So this is natural, of course, it's e. But that one does not have 10 in the extra base, so it's neither nor. Very good question, actually. Thank you. The second one is natural, but the first one is not common and is not natural.
So this is okay.
Some other base. It's not one of the two special ones. Believe it or not. Okay. Ready to continue? Let's identify each and every item here. So P is the principal. We can take a loan or we can deposit money. Principal. A is the accumulated value. I borrow $100 from you today, and I have it. You're saying, okay, you have to pay me back 2%. So in 10 years from now, I will have to pay you back the accumulated value. If I deposit money, then the bank will give us back, or we deposit money, will give us back the accumulated value in time. R, annual interest rate. Annual interest rate. T, time in years. What else is there? N, number of times interest is compounded per year. Okay, so here's a problem that we would like to work on. Let's say 54. On page 475. Find the accumulated value of an investment, $5,000, 10 years, an annual interest rate of 6.5%. If the money is part A, semi-annually, quarterly, monthly, and continuously. Let's identify each and every item. What does 5,000 represent?
The accumulated value? No.
What is 5,000? Principal, very good. What is 10 years? Very good. What is 6.5, which cannot be used? It has to be 0.065. Very good. And what does semi-annually mean? Very good. What does quarterly mean? Very good. What does monthly mean? And this is by itself continuously a totally different formula. So this is for continuous, and this is n times a year. Okay, as you see, there is no n in here. N times per year. So let's copy the formula. So we have A equals 5,000, 1 plus 0.065 divided by, in the calculator I don't have n, so I'm going to put x, raised to 10x. Let's look at the formula one more time. I replace the principal by 5,000. I copy the 1 plus. I replace the annual interest rate by 0.065. I replaced n because I have 2, 4, 12, and I want to put it in the calculator. And t's got replaced by 10, and then n is the same x. You don't have to change it to x. I put x just to refresh our memory that we do not have n in the calculator, so we have to go to y equals. So go to y equals, clear whatever you have, and we're going to punch in 5,000, in parentheses 1 plus 0.065 divided by x, close the parenthesis, put a caret, and in parentheses 10x. Once we have all this, I go to second and table, and what do I plug in? I plug in 2. I plug in 4. I plug in, very good. Only because I didn't want to repeat. Do you have to do this? No, but it's easier if you do. If you agree with putting in the function in. And then you still have to go and highlight it because of the rounding error. So I'm going to say A of 2 is $9,479.19. A of 4, scroll down to A of 4, $9,527.79. A of 12, scroll down to A of 12, $9,560.92. And now we need a second formula for continuous compounded interest. So let's go to, you can get out of there, 5,000. Remember E, second and natural log. And in parentheses, I have 0.065 times 10. Close the parenthesis and press enter. So for the interest compounded continuously, we have A equals 9,577.70. Oh, I'm sorry. 5,000 times E to 0.065 times 10, and we get this. Any? Yes, please. Patricia, go ahead.
Okay, so can you help me? I just didn't know how to do the little 10x, how you're doing the small little parentheses. I wasn't exactly sure. But the
Yeah.
caret,
Yeah, so you just have 10x and close the parenthesis.
it's not sure.
Yeah.
Oh,
So then you have 2 and 4 and 12. Not sure, but it works. And then you have to create a new, are we okay here?
no, I got confused.
Yeah, just plug in 5,000. And then second and natural log, which is e to the x. And parentheses. Your calculator may be sophisticated.
Oh, okay.
Yeah, so we don't need parentheses for the power, but I always put it. If it's an operation that we have to, something that needs to be performed there, I would always recommend parentheses. Although these new calculators may not require that. Are we okay with this? Everyone? Yes? Charisse? Yes? Perfect. Good. So you're not, I think it's a lot of information, but we're going to repeat this and repeat this. I don't think you're going to find chapter 4 too involving. Yes, there are 2 new functions. We've never seen something like this before, right? With a horizontal asymptote and one end. But the whole thing is going to be the same theme you're going to see. Okay, 4.2, logarithmic function. We already graphed it. When? Just a few minutes ago. When we put the inverse function. Exactly. So here's one graph with a base greater than 1. And here's another graph with a base less than 1. Ready to continue? So let's graph them. I will graph them again. So here's one, and here's the other. So we established that if the base is greater than 1, the function will be increasing or decreasing.
Greater than 1,
Yes.
decreasing.
Greater than 1, always nice increasing.
Okay.
If the base is less than 1, it will always be decreasing. So here is the log function with base greater than 1. Here's the notation. I'm going to write it, and in words also. This is f of x log base 2 of x. The notation is somewhat special, interesting. Here's how we read this. Log base 2 of x. And here's the other one. Can anyone give us this function? So here the base is greater than 1, and here the base is between 0 and 1. Can anyone give us this function that we graphed a few minutes ago?
Negative.
There is no base with negative.
Oh,
So I have to write log base. This was 2, increasing. This has to be a base less than 1. Exactly, that's what we graphed a few minutes ago. We graph log base 1/2 of x. So here's how we read this. Log base 1/2 of x. Okay, so what do we have to remember about the domain of this function, the pure log function, always, forever? That it's not a friendly function. We wish it were, but it isn't. But what is its domain then? 0 to infinity. Very good. It's not even 0, right? The square root, we were able to plug in 0. This one cannot even take 0. Why? What is this? What is this? Vertical asymptote at 0. So x equals 0, VA. X equals 0, VA. That's why it cannot even take 0. Okay. Now I have to task myself with convincing you of how this works. But before that, I'm going to say very, very important concept. Very, very important concept in this chapter. Here is the concept in plain English. Any log equation can be replaced by an exponential equation. Comma, and vice versa. And you could say, okay, what's the big deal here? So what? That any log equation can be replaced by an exponential, and any exponential can be replaced by a log equation. What's the big deal? Here's the big deal. First of all, let's see how we explain this or present this in math terms. Log base a of x is a number y. This is a log equation. I am going to write a symbol that is called double equivalency symbol. So why is this double equivalent? What does it mean? It means that I can start with a log and present an exponential, or I can start with an exponential and present a log. It goes both ways. So careful how we do this. We always start with the base. We start with the base and we go counterclockwise. A raised to y equals x. So this is an exponential equation. So if I start with log base a of x is y, then this whole thing can be replaced by this, by the exponential equation, a raised to y equals x. So let's see what this is telling us. Let's use it now. So here's an exponential function. Can anyone give us any exponential function you can think of?
3. I mean,
Yes, very good. 3 to the x. Awesome. So let's say x equals -2, x equals 0, and x equals 3. Can anyone give us the y values, the coordinates, and the other set? So please plug in -2 and tell me what to write.
yeah.
Write it on the side. 3 to -2 is 1/3 squared, which is 1/9. You don't have to do this in your head. So it's 1/9. When x is 0, what do we get? Excellent. When x is 3, what do we get? Excellent. So what do I have to show you now that the inverse function will do? First of all, can anyone give us the inverse function of 3 to the x? The name. Let's go back. Let's go back. This function was 2 to the x. Its inverse was?
1. Oh, yeah.
Its inverse was?
Oh, it was the one above 1.
So this was f of x. This was f of x. I should graph it here. This is 2 to the x, not over there. This is the log function. So then what is the inverse of 2 to the x? Log base. So the inverse of an exponential function has to have the word log in it, right? Exponential and log are inverses of each other. So if the exponential is 2 to the x, the inverse function must be log base 2 of x. What was the exponential function here? The exponential function was 1/2 to the x. What is the inverse function of 1/2 to the x? The function must have the word log in it. Log base 1/2 of x. Okay, now, coming back to the function we just created, 3 to the x. What is the inverse function of 3 to the x?
Log.
Very good. Log base 3 of, excellent. So what do I have to show you now? I have to convince you, that's my task. I have to convince you that when I apply log base 3 to 1/9, the answer must be and will be -2. Otherwise, the whole thing fails. Then I have to show you that log base 3 of 1 must give only one answer. What answer? Excellent. And log base 3 applied to 27 must give only one answer. Which one? Yes, and I have not convinced you of it, but I am going to use this, and I think I will convince you. Okay, so we are trying to calculate log base 3 of 1/9. We are going to try to calculate log base 3 of 1 and log base 3 of 27. Ready? No calculator will do that. Don't try. Okay, so log base 3 of 1/9. Log base 3 of 1/9. Log base 3 of 1/9 is a number. I have no idea what it is, but I know that this is equivalent to 3 counterclockwise raised to whatever equals
2, -2.
1/9. One more time. Let's do this because till we get used to it. 3 raised to whatever equals 1/9. 3 raised to whatever equals 1/9. Correct? Good. What could this number be? Can it be 5? No. Can it be -1? No. Can it be 0? No. What is the only number that it can be? Do you agree with -2? Because only 3 to -2 is 1/9. I hope I convinced you that 1/9 will go back, 1/9 will go back to -2. Okay, the next one. Log base 3 of 1. I have no idea what this is, but I know that I can change it into an exponential equation. Can anyone try? Always start with the base. Counterclockwise. 3 raised to whatever equals 1. What can be the whatever? It can only be, yes, it must be 0. So I think we are convinced now that 1 goes back to 0 through the log base 3 of x. Okay, one last one here. Log base 3 of 27. I have no idea what this is, but I know that any log equation can be replaced by an exponential one. How? For this one. Always start with the base and go counterclockwise. 3 raised to, I'm not sure what, equals 27. What can this be and no other number? It must be 3, because 3 to the 3rd power is 27. So therefore, 27 through this function indeed goes back to 3. Any questions? Any questions? I would like us to look at a couple of examples with domain and then a word problem. Okay, so let's look at problem 76 on 490. F of x equals log base 5 applied to x plus 6. We're not asked to do anything to this function or with this function. The only question here is find the domain. What do I have to write? Yes, let me refresh your memory. If we have a function that is the square root of x minus 3, what do I have to write just to find the domain? X minus 3 must be greater than or equal to 0. So then x greater or equal to 3, so that the domain must be 3 to infinity. Okay? In the same way, what am I applying log to? I'm applying log to x plus 6. I know that the expression that I apply log to must be strictly positive, like the expression I apply square root to must be positive or 0. So what do I have to write? In the same way as I determine the domain for the square root, what do I have to write for this function?
X plus 6 is greater than or equal to
Just greater than. Excellent. That's the idea. It's a very good comparison, but just be careful. Here I can have 0, here I cannot. So then x must be greater to greater than -6. Domain -6 to infinity, and it's done. You don't have to do anything to the function. You're only asked for the domain. Let's look at one more, like 78. And then we'll look at a word problem. So we have f of x equals. This time we have just log. And I would like to mention, I did, but I didn't put it in writing, special log functions. Here is the common log, logx. We don't see any base. It is assumed to be 0. You know what I mean, 10, not 0. For the natural, the convention is ln, natural log. And it is assumed, what do you think the base will be? Same base with the natural exponential function. What was it? E, very good, awesome. So if you do not see a base and you see ln, it means natural, which means base e. If you see log with no base, of course you know the base is 10. So here we don't see any base, we know it's 10. By convention, we don't write it. The same question again, we are asked to find the domain of this function. What do I write and solve to find the domain? I have to write 7 minus x. That's what I apply log to. Must be greater than 0 indeed. That's all I need to write. Negative x greater than negative 7. Remember, I have to multiply or divide by negative 1. What happens when I do that? Very good, awesome. So the domain will be negative infinity 7, and it's done. Okay, let's look at a word problem, and then we'll stop. Page 491, problem 119. 491, let's read it. Students in a psychology class took a final exam. As part of an experiment to see how much of the course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. The average score for the group, f of t, average score, is given 88 minus 15 times natural log of t plus 1. This is ln. ln. What is the base of ln? E, very good. And time is between 0 and 12 months. Can anyone give us an idea of what function is this? We are given 88 minus 15 ln, parentheses, t plus 1. What type of function is it? Is it rational? Is it radical? It's natural log. Yeah. Natural log. It has a natural log in it. So it's a natural log function. Very good. 0 to 12. Yes, 0 to 12. T is between 0 months and 12 months. Perfect. So now they want us to find what was the average score on the original exam. Original. I'll ask you in a moment what that means. What was the average score after 2 months? 2, 4, 6, 8, 10, and 12 months after a year. Sketch the graph, describe what the graph indicates. Perfect. When we're asked about original, what do you think that means? Original. The day somebody's born, it's like original day. How much is time for original? 0. Very good. So in part A, we're asked to find f of 0. In part B, of course, f of 2, f of 4, f of 6, f of 8, f of 10, f of 12. And in part C, they're asking us to graph. Let's put the function in. We're not going to do this piece by piece. We're going to put the whole thing in y equals. So 88 minus 15 ln, natural log, in parentheses, x plus 1. So 88 minus 15, natural log, x plus 1. I have 2 parentheses there, sorry. Careful, don't do that. There's no need. It pops up with a parenthesis, with one of them. Ready? second and table, we want to plug in 0 and 2 and 4 and 6 and 8 and 10 and 12. Answer in percent: 88%, 72%,
60,
64%.
59%,
Very good. 59%.
55%.
Excellent.
52%.
Yes.
And 50%.
And 50%. It appears that they got an 88% average score, but as time progressed, what happened to their knowledge a month and a year later? It dropped from 88% to 50%. Very good. So now let's graph. I want the viewing window to be between 0 and 12. So 0, 12 with a scale of 2. So 0, 12 with a scale of 2. And the y, of course, I'm looking at the y values. So I'm going to say maybe 0 to 100 with a scale of 20. So in y equals, we have the function. So just go to the viewing window. And 0, 12 with a scale of 2. And y minimum 0 is okay. 100 with a scale of 20. And just hit graph. And here's the graph. It's coming from the original of 88, and it's dropping surely to what? 12 months later to what?
50.
50%. So this was an example in which